And welcome to 18-2, where we're going to be talking about reversible reactions and equilibrium. A reversible reaction is one in which, let's go ahead and define this. It's a reaction in which the conversion of reactant to product and the conversion of product back to the reactant occur at the same time. Alright, so let's take a look at a reaction that does a pretty good job of illustrating that. Is this reaction overall where you take sulfur dioxide and oxygen to form sulfur trioxide. Now, typically what you do is you start right here where you have sulfur dioxide and oxygen, which are the reactants, and then of course it's going to move towards your product, your sulfur trioxide. But if you notice where the reaction stops, you have a mixture of both sulfur trioxide, which is our product here, which is right here, 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 and here. You also have in this mixture some sulfur dioxide, SO2, left right here and here. Let me circle those, here and here. And then you also have this lone oxygen left right here. So not all of the reactants get turned into product. Why is that? Well, what can happen is, looking at this box over here, some of the product will actually turn back into reactant. Some of the sulfur trioxides will collide and reform SO2 and O2. And so both the forward reaction and the reverse reaction are going to occur at the same time. Now, looking at the middle of our page here, let's take a look at this same reaction graphically. Let's take a look at the one on the left. This one starts with only SO2 and O2. Alright? Notice you have your SO2 starting right there, you have your O2 starting right there, your SO3, which is starting right there, is starting at 0. So what happens is, over time, as the SO2 concentration decreases and your oxygen decreases. Now, why are they decreasing? Because they're colliding and they're reacting. So as those two decrease, the forward reaction slows. Why does it slow down? Well, as you use up your reactants, they collide less frequently. As they collide less frequently, the reaction simply slows down. On the other hand, initially there's absolutely no reverse reaction because there's no product to collide. But as the product concentration, which is SO3, as that increases, then the reverse reaction speeds up. So the forward reaction is slowing down, the reverse reaction is speeding up, and eventually notice that right here, here, and here, and it actually planes out right about there. There's absolutely no change in concentration of anything. Why? Because the forward reaction is going at the exact same rate as the reverse reaction. So just as many SO3s are forming as SO3s are going back to reactants. Now, let's take a look at scenario 2, where you start with only product, which is SO3. If you start with only SO3, notice it's up here, You have SO3, which is product. Both our reactants are at 0. Well, what's going to happen is that the reverse reaction is going to occur. As the reverse reaction occurs, the SO3 decreases. They're colliding with one another, and our SO2 and O2 are going to be increasing. Also notice, and this is something that's noteworthy to write down, so notice that at equilibrium, the relative amounts of reactant and product are the same regardless of the original condition. So if I start with, over here at number 1, if I start with all reactant but no product, I end with a certain amount of SO3, SO2, and O2. Notice if I, in number 2 here, if I start with all product but no reactant, I'm going to end with the exact same amount of SO3, SO2, and O2 regardless of how I started the reaction. Notice these are all at the same relative values. And so the deal with equilibrium is that it doesn't matter how you start the system, it's always going to end with the same relative amounts of reactants and products. Now it won't be the exact same number, it's just the same ratios of the reactants and products. If you start with just a little bit of reactant, you're only going to get a little bit of product. If you start with a lot of reactant, you get a lot of product. But the ratios would be the same regardless of how much and how you start this thing. And equilibrium is simply defined as the point at which the forward reaction rate equals the reverse reaction rate. At that point, the reaction looks stopped, but the particles are still interacting. Interacting, not interaction, interacting. There we go. And we call this a dynamic equilibrium. Dynamic refers to the fact that there is still movement going on, as opposed to what's called static. You have static electricity where the electricity doesn't move. Dynamic electricity, I guess for lack of a better term, would be where you have electricity that's that is actually currently in motion. All right. Now, in terms of a dynamic equilibrium, it would look something like this. If I scroll back up to the top and show you some pictures of molecules, if I traced and let's go ahead and get a new color here. Let's go with kind of this teal color. All right. If we trace this particular molecule, that might collide with an oxygen here to reform or to form, say, this sulfur trioxide. At equilibrium, the numbers of particles are not going to change. However, what can happen is that this sulfur trioxide turns back into oxygen and sulfur dioxide, and a different set of SO2 and O2 turn into the sulfur trioxide. So the actual numbers are not changing, but the individuals are. It's analogous to, say, the change over in first and second shifts at a factory. Say you have 100 people that work on first shift and 100 people that work on at second shift. Well, at the end of the shift, the first 100 go home, the second 100 come on, but at any given point you still have 100. So it doesn't, in terms of the numbers, you have the same number of workers, but the actual number of workers don't change. Okay? We'll continue this discussion in the next podcast.